Okay, good morning, everyone. So last week we have already introduced the purpose why we need to have to learn the quantum mechanics, and we introduced the questions that we need to use quantum mechanics to help us to understand. And also we have introduced wave equation, and with some of the consideration, and finally we can come up with the most important physical implications that coming from the wave equation is that the wave equation, the wave function is a probability density function and is independent of the time. And one major difference between classical and quantum mechanics is that the classical mechanics, the position of a particle body can be determined precisely. But however, we should consider the case that the quantum mechanics, the position of a particle is found in terms of a probability, which means that we can only use probability to estimate a carrier rather than to determine the location precisely. So, to further solve the questions that we might already introduce, then therefore we also have to talk about the boundary condition. So since this represents a probability density function, so which means that the integration of this function, between minus and positive infinite will be equal to 1. So because of the overall probability will be equal to 1 if we do the integration for all times of the space region. And the wave function and its first derivative might have the following properties if the total energy E and the potential Vx are finite everywhere. So the first one is a derivative. Derivative of x of the wave function versus x must be finite, single value, and continuous. And second one is the wave function also must be finite, single value, and continuous. So here is some of the possible example of a potential function and the corresponding wave solution. So in the case A, the wave function is finite everywhere. Then the wave function as well as its derivative is continuous. And the second one is the potential function is infinite for the case with here and here. And the wave function is still continuous at the boundary, but the first derivative is discontinuous. So we have these two boundary conditions that help us to later to solve the issues that we want to understand. So the first one is something that we have been mentioned, that in here we consider the electron in the free space where we have one electron here and free moving in this space toward the positive x direction and negative x direction. And to consider the free space, so first we made several assumptions. That the first one is the energy and also the potential Vx versus x position is constant. So this is our Vx here. This is our Vx. And therefore we apply the last week what we already derived this equation. But now, because this is a free space, so we can assume that this can be approached to 0, right? Because of this is a free space. So inside the free space, we consider the potential will be equal to 0. And therefore, this equation can be simplified as here. And with considering this equation, we can generally to have the solution phi x can be represented as this one. This is something that we learn from the engineering mathematics with considering this kind of equation. We can generally to assume that our solution can be expressed like this one. And since this is a time-dependent portion of the solution, therefore phi t can be also expressed as an exponential and will be equal to exponential minus j omega t here. And therefore, we can consider this phi with space and time can consider as a separation variable where will be equal to space only versus the time dependent only. And since right now the phi t is equal to this one, and therefore this equation can be further derived as a phi x minus exponential minus j omega t here. And now we can have this general solution for phi x t here. And with considering this equation, also this one here, with here, this is our phi x here. So therefore, we can have derive come back as a x and t dependency, which will be equal to this one. So the phi x t now, the original we consider as a time independent, but now we're using the separation variable, and this one is equal to this one, and therefore this one is equal to this one, and this one we're putting back here, and therefore we can have this general solution of a wave function depends on the x and t here. And therefore, with considering this equation, the first of all, the k means a wave number. The k is a wave number, which is equal to this one. And also the most important is that this equation suggests that the a is a wave function traveling in the positive x direction. And while the second term, the b is a wave travel is a the coefficient b is a wave traveling in the minus x direction. So therefore, with considering the quantum mechanics and wave Schrödinger's wave equation, so we can realize that once you have the electrons inside the one free space, the electron can only flow toward the positive x direction, and also the negative x direction. So which is pretty makes sense that if right now you don't consider all of these calculation, you can still imagine that the one carriers inside the free space, for sure that we can only have the two possibility of this carrier movement. one is moving in the x direction, and then also the possibility is the carrier, the electron moving in the negative x direction. But now we have the solid proof. We can use quantum mechanics. We can use the wave equation to further confirm our speculation of this pretty straightforward behavior that can be confirmed by using this calculation. So in the end, as I already said from last time, that when we try to use this wave equation of quantum mechanics, it's not trying to make that us getting more trouble. It's not trying to complicate the earth. It's just trying to prove that what we guess here. So we can already guess that there's a free carrier, there's a one electron in the free space must behave like this two possible moving direction. Now we have the very strong provement coming from these mathematics calculations. So that's the first case. That's how we actually application of this wave equation to state by state to solve our questions. So next one, we're moving to the next question is, as we already mentioned last time, that if we consider there's an infinite potential well, so the particle is assumed to exist in region 2. So the particle is contained with a finite region of space, which is this one. So in region 2, as a similar, we first to apply the time-independent wave equation. Now in the region 2, we only consider the case of region 2, where our potential Vx is equal to 0. So once our Vx is equal to 0, and again, we can simplify as our wave equation become like in this form. And the particular form of this solution can be written as shown in here, where phi x is equal to a1 cosine akx plus a2 sine kx here. And now we consider the boundary condition where wave function at the x equal to 0, and then the wave function at the x equal to a is equal to 0 is in here. Boundary condition here should be still considered as a 0. So therefore, we can start to solve this wave equation where we get the phi x equal to a equal to 0 will be equal to a2 sine ka. And with trying to apply this boundary condition, now we can get the wave equation will be equal to this one, which suggests that this should be the standing wave. Right, so this is something, the very similar form that we have learned when we have a high school physics, when we talk about the oscillation of the one string, that we see also the standing wave, right? So this is same thing that can be considered in this case. So in this case, that we have inside this region, we can start to understand that our electrons will behave like a standing wave in the region 2. And now, furthermore, we consider for this boundary condition. So now we can also try to solve the k value here, which will be equal to n pi over a, and also the k is equal to this one where we derived before. Therefore, we can start to realize that the En, the energy of these electrons, which is become as a discrete, which means that each n will corresponding to the one energy level. So the energy inside this region 2 is not continuous anymore. It has a discrete energy level, which means if we have the E1, therefore we have a one discrete energy where h bar square 1 square pi square. So that's a one discrete energy level. And also we have another discrete E2 is equal to this one, which means this becomes the value like this one. So this also suggests that in this case, with the electron confined inside this potential well, the electron will behave like the standing wave. Furthermore, the energy for this electron is not continuous anymore. It's become the discrete energy. That's become the foundation of the concept that we call the quantization of energy. So the energy of the particle is become quantized. So quantized means that we can specifically have the energy of the 1 electron volt, 2 electron volt, 3 electron volt. That's all. It's not a continuous distribution. It's a quantized. It has a specific number here. That is, the energy of particle can only have the particular discrete values. So this become later, which when we all consider the electron, we can specifically have the energy for the electron in the certain of the potential well. Because now from this calculation, we can understand that the energy itself has a particular discrete value, and the energy of particle is quantized. So that's a pretty important information we can get it from this case. So far, the calculation is very simple. It's just use what we have learned. There's nothing that we needed for the very complicated equation calculation, but the conclusion is getting more important because we get the conclusion like the ones you have a particle inside this potential well. So we get the first conclusion is that the electron will behave like a standing wave, and also the energy is quantized, and the energy has discrete energy values. Okay, so that's a second case that how we apply this wave equation to solve the certain realistic issues. Then the third one is that the state potential function. This is what we already talked about in last time. That in this case we consider a flux of the particles. A flux of particles incident on the potential barrier. On the potential barrier, which means that right now we consider that there's one incident particle will be injected from left to the right and then face as a region 2 that has a potential barrier of the V0. So now, again, similar things, what we'll do is we will try to solve the wave equation in the different region. And the first one is a wave equation in the region 1, which is here. So now again, we apply the time-independent wave equation here. Then we consider as inside the region 1, the potential is equal to 0. And therefore, we get this simplified wave equation. And now again, this wave equation has a general solution as shown in here. And then this general solution suggests that this is a traveling wave as a A1 here, exponential jk1x. That suggests that we have a traveling wave. We have a traveling wave in the positive x direction. So that's our incident wave. So which means that once you have incident particles toward this barrier, then we can foresee that the electrons can be moving toward the right with a positive x as a traveling wave. And similarly, this also suggests that there is a traveling wave in the minus x direction. A traveling wave in the minus x direction. So which suggests that once you have an incident particle toward to this potential barrier, we will first to see the traveling wave in the x direction. Then we can also see the traveling wave in the minus x direction. I think so far, all the physics phenomena are pretty straightforward and pretty much make sense. That's all aligned what we already have learned, and then that's all aligned what we can imagine. It's nothing like the very complex physics that beyond our imagination. This is pretty like the common sense that you have the incident particles toward this barrier. For sure that we can see the electron traveling toward the right, and then we can also expect that there's reflections. Therefore, there's a traveling wave toward the left. So that's the pretty common sense physics phenomenon that we can already imagine. But now we have the getting more as the solid proof from based on this rigorous of the Schrödinger's wave equation. So we can also have this equation here to prove what we speculate here. And also I believe that so far the calculation is not that complicated. This is all the calculation so far is just based on the knowledge that you have been learned. I'm not sure that for your generation whether you have seen this equation before. At least in my age, that in the high school, in the third year high school, I have already seen this equation that has a positive and negative wave showing us a positive x or negative x direction. But in anyhow, if you don't if you haven't learned from the high school, I think in the first year of general physics, you should also learn about this. Okay. So some information that we are interested in. We are now understand the situation in the region 1. For sure, the next question is we are interested in the phenomenon that will be happen in the region 2. So in the region 2, this is not an infinite potential. There's a fixed potential here where we consider the V is equal to V0. So that's the region 2 that we have this potential barrier V0 as well. Still the same. First, we apply this time-independent wave equation, but now we make the assumption that our energy is smaller than this barrier, which is pretty makes sense that because if this is energy larger than this barrier, for sure that your incident particle should be possibly directly overcome this barrier. So we are interested in is that if your energy is smaller than barrier, incident on this barrier, and what will be happen in the region 2 here. So we have these equations, and then we can have this general solution for the phi 2 here. And one thing that particularly worth mentioning that the wave function must remain finite. But now this is one coefficient times exponential positive x, which means that this term will lead to the infinite because of this is a positive exponential. So therefore, this must be equal to 0. So the coefficient, because this remain finite, so the coefficient B2 must be equal to 0. Otherwise, we will get the non-reasonable wave equation here. And therefore, the equation here can be further simplified as here, which is also very simple equation to describe the wave behavior in the region 2. So now, we summarize what we get is so far. We have a region 1 where you have the wave equation as an incident particle towards a positive x direction and negative x direction, and then wave equation the wave equation in region 2 will be equal to this one. So next step is that we will apply the boundary condition to solve this coefficient. So the wave function at x equal to 0 must be continuous. Therefore, these two should be equal to together because it must be continuous at this interface. It must be continuous at this interface. And also, since the potential function is everywhere finite, so the first derivative of a wave function must also be continuous. Therefore, we have this one. So with considering these two boundary conditions, so finally we can get the correlation between the B1, A1, and the A2 and A1 here. So that's in my class I try to avoid the like step by step to calculate, to guide you the calculation, because I believe this calculation that you can work on by yourself. It's not that difficult. I think most important still will be the physics meaning and the physics implication. That once you understand the physics, you won't forget it. But for this mathematical equation, you probably can memorize during the class. But I believe after 1 year, 2 years, 5 years, you won't remember the equation. But physics will live in your mind forever. Okay. So once we have this coefficient and once we have this wave equation, so now we start to consider the flux of the incident particle can be derived here. This is equation for the flux of the incident particle, and this is a flux of a refraction particles here. So therefore we can have the one very interesting coefficient that we call the refraction coefficient, which means that we consider as electrons moving toward this barrier, and there will be the certain reflections happen here. So that is we consider the reflection. So therefore we can define this reflection coefficient here. So in the region 1, the reflection coefficient can be estimated as here. And then the result of the 1 implies that all of the particle incident on the potential barrier for the case where energy is smaller than this potential V0 are eventually reflected. Right, so that's very consistent with our classical physics. So you try to throw the 5 balls towards the wall, then you will get the 5 balls bouncing back. You get the reflection of 5 balls. So that's exactly the same like the classical physics. So the most cool things by using this wave equation is that the certain case that we can, although beginning it looks like very complicated, in the end with a certain calculation, a certain of the consideration, finally it can be simplified as a case like the classical physics that we have a 100% of the reflection. That's very consistent with the classical physics. But the next one, again, if we consider as a region 2, so we can have the further information derived here. So for the case of energy smaller than V0, actually we will see that what the wave equation tells us is that the coefficient of A2 is not 0. So if A2 is not 0, then the probability density function of the particle being found in region 2 is also not equal to 0 here. Because A2 is not equal to 0, so we already have the equation to prove that inside the region 2 there's a wave equation. But because we have a wave equation, that means that the probability density function inside the region 2 is not also 0. And this result implies that there is a probability. There is a finite probability there's a probability that the incident particle will penetrate the potential barrier and exist in region 2. This is something very important. This is only can be proved once we consider the quantum mechanics, once we consider the wave equation. So the probability of the particle penetrating the potential barrier is another difference between the classical and quantum mechanics. So, of course, in the classical physics, we can only know our balls can only exist in the region 1. There's no chance that we will find the ball inside the barrier, inside the wall. But now if we switch to quantum mechanics, we can foresee there is a probability to find your carrier, your electrons, in this potential barrier here. So that's the main difference between the classical and also the quantum mechanics. And this is very important because this actually is help us to understand that if you consider the real device schematic where we have the source where we consider as a MOSFET, where we have the source and drain, and now we have the dielectrics. And then on top dielectric, we have the gate electrode. So now if we apply the gate voltage here, and then we start to have the attractive electrons in the channel. And this, in the end, based on this wave equation, the conclusion tells us that you will see the electrons is possibly being penetrated and existed inside this barrier, which is a dielectric. Which means that the electrons inside this barrier, which is our dielectric. This phenomenon, if you already have the experience for the semiconductor characterization, probably it's not surprised that you will very often be told that there's a gate current. But now we have this solid equation to prove that it's indeed that the electron can certainly still exist inside this dielectric with a certain probability. So that's the very important conclusion that's coming from the quantum mechanics, coming from the wave equation. Okay, so let's move for the last case. The last case is we consider only the barriers, potential barrier in the region 2, and then also similarly, we have the potential barrier, and now we try to understand the phenomenon that we call the tunneling. So, solve still the time-independent wave equation in each of the 3 regions. So this is the same that what we are doing for the previous case, that we just try to solve we apply the wave equation in a different region, consider the different boundary condition, different potential, and therefore we can expect that we have this general solution for the wave equation for the phi 1, phi 2, and phi 3 here. And we can also define as a coefficient that we call the transmission coefficient. Since the potential V equal to 0 in both region 1 and region 3 here, so the incident and then the transmit velocity are equal. And right now we consider as a very special case where energy is much smaller than V0 here. So we get the transmission coefficient as shown like this one. So that's still the same conclusion where we derived before that this equation tells us that there is a finite probability that a particle impinging a potential barrier and will penetrate the barrier and will appear in region 3. So this phenomenon that where we already brief discussed in the first slide that once we have the incident particles here and moving toward as a potential barrier, and then the conclusion is that we will see the certain particle can still be existed in the region 3, and this phenomenon is considered as this transmission, and therefore we call this as a tunneling. So that's in the end, this is the most realistic case that we will see in our semiconductor device. But with the step-by-step between from the question 1, the case 1, case 2, case 3, I believe that now if we look at the realistic case like the case 4, the conclusion is very straightforward that we have the incident particle that be possible be existing in the region 2, but also being possible penetrated and existed in the region 3. And this phenomenon is what we call the tunneling. So all this calculation just try to prove that our physics-based understanding that in the beginning we already guess that to further understand as a transistor, a device operation, we can see there's a leakage current, there's a carrier in some region, and we guess that the carrier, the electron, might be able to tunnel to reach to the other side. And finally, with all this wave equation and quantum mechanics help, that finally we can get this as a mathematical proof. So again, this equation is not that try to complicate us. This equation just try to help us to prove that our speculation is correct. And once our speculation is correct, then the proving procedure for this by using this equation probably is not that important. Important is that the physics-based understanding. So we can also extend this to the case that we consider as sphere coordinates here. Therefore, the equation can be rewritten as follows. And now still we have to use a separation of variable techniques. That will become the 3 different variables here. So of course we won't spend the time to derive. We just quickly go through this case, and then with considering this case that finally we can also have this quantum number which consider the NLM, and each set of a quantum number corresponds to a quantum state that the electron might occupy, and therefore the electron energy is shown in here, which each N will still corresponding to the one energy. So that's the same conclusion where we already derived before, but now just extend to the sphere coordination. So similarly, the initial portion of the periodic table's element might be determined by using the result of the one electron atom plus two additional concepts, which is electron spin and also the Pauli exclusion principle, and therefore we will have these four basic quantum numbers here. So finally, just give you as an example that what we learn from the knowledge coming from the chapter, that's already enough for you to understand this very classical epic paper. This is paper a little bit old. This is published in 2001, February 2001. This is in the very famous Journal of Applied Physics, and this paper was talking about the gate current, tunneling current in the ultra-thin metal oxide silicon transistor. So now, right now you see the title, probably that's already a little bit familiar with you, because this paper is talking about the gate tunneling current in the MOS transistor. And this paper was published by the two authors. This one is a Professor Zhitang Sa, who is later become the inventor of the CMOS, Sa Zhitang. And then so he is later become the inventor of the CMOS, which proposed as a PMOS plus a MOS. So that's become the foundation of our logic component. And then the first author, Jin Cai, now is a director in the TSMC. So he is working in TSMC for many years. So, but you can still see in their early times work, 2001, that they are working on how to understand the gate tunneling current in the MOS transistor. And just quickly show several key figures here. So you can see the key figure here. I believe the key figure here is not that difficult for you, because what they try to draw here, which is a wave function, right? So this is a wave function in the region 1, in the region 2, and also in the region 3. So they also use a wave function as a very basic, try to step by step to the right to understand the gate tunneling current. But in this case, it's in the ultra-thin oxide. So in here, the ultra-thin oxide means this is a less than 3 nanometer thickness. So we can quickly go through the abstract together, and this you get a sense that what is normally this paper is talking about. So gate carrier tunneling through ultra-thin 1 to 3 nanometer silicon dioxide layer in the MOS structure is investigated using this transition probability method. So now you see the several keywords that I already mentioned. The first one is tunneling, and then the second one is probability, right? You see that we need to use a probability to understand. And the quantum mechanics wave function matching and the two abrupt potential boundary of this trapezoidal silicon dioxide silicon barrier gives an electric field dependent pre-exponent factor in the WKB tunneling probability, which significantly affects the current voltage characteristic at the low field. Of course, what they say here is pretty complicated, but you just need to recognize with the current knowledge you have, you just need to recognize that he used quantum mechanics, try to understand this tunneling probability, and in the end, this tunneling probability will significantly affect the current voltage characteristic at the low field. So let's just look at this figure 2, which I think is very important. this is a tunneling current versus electrical field. So now we can see this is a tunneling current comparison with 2 nanometer and 5 nanometer here. So now you can see with reducing the dielectric thickness from 5 to 2 nanometer, the tunneling current is highly increased. Original was around in the order between 10 to minus 18 to 10 to minus 22. But now, once we reduce our dielectric thickness from 5 to 2, then the tunneling current is increased beyond the 10 to minus 6 here. So this becomes a significant warning for the people who is doing the semiconductor scaling, because that means that if we keep him reducing the oxide thickness, we will face a very high tunneling current. So once we have the high tunneling current, that also suggests that we have very high gate current, right? So because based on my previous drawing, that once you apply the gate bias, you have the electron will tunnel through the dielectric, becomes the high gate current. This becomes the critical concern of the whether we can continue to do the oxide scaling or not. Because this is 2001. 2001, they already work on the 2 nanometer. If you are already have the semiconductor device fabrication in the TSI, in the NFC or whatever, you probably know that in the most of the case that in university, what we are working on, probably still like a 5 nanometer, 3 nanometer, sometimes 10 nanometer, 2 nanometer is difficult to fabricate unless we have the very special machine like the atomic layer deposition, so we can make this as a very thin, like 1 nanometer, 2 nanometer. But in the 2001, there's already proof that if we scale down to 2 nanometer, the leak current is so high, therefore the device will become really there's a loss of reliability concern for the semiconductor device with such a thin dielectric, and therefore we cannot continue to have this oxide scaling anymore. So this actually in the end become as a key concern around the 2000, that how to solve this oxide scaling issue. How do we can make it to avoid this leakage current, but at the meantime we can keep reducing the oxide thickness. So that's why later you will see the solution. I can tell you the solution how to avoid these issues. In the end, we propose to have this high K metal gate. So with help of a high K, we can avoid to make our dielectric very thin, but we have the equilibrium oxide thickness can be very thin, but the physical thickness can be thicker. In here, I won't talk about too much about the high K metal gate, just to let you know that the 2000 is a starting point. People start think about we cannot keep in scaling the silicon dioxide, but what would be the solution, active solution that can address this issue? And that's why people start to propose as a high K as an alternative here. Okay, so let's just look at the key takeaway for this chapter. First, we talk about the quantum mechanics. quantum mechanics require to describe the electron behavior in the very small scale system, for example, the semiconductor, and also the energy is quantized, so the electron can only occupy discrete energy level. And also we have considered this wave-particle duality, where electron exhibit both like the wave but the particle. And we also consider this uncertain principle, and the implication is that the classical mechanics cannot accurately describe electron behavior at a very small scale. That's why we need to have this quantum mechanics. And we start to apply this Schrödinger's wave equation. This is a fundamental equation used to describe the electron motion in the quantum system. And we also indicate the wave function, which is considered as a probability of finding an electron. And probability density function determine where electrons are most likely located, just most likely, which is probability, cannot precisely determine. And once we apply in quantum mechanics and lead to the several key phenomena, this one is the energy quantization and also the quantum tunneling. And then the implication is that the quantum effects from physics foundation forms the physics foundation of the modern semiconductor device and nano electronics. That's why the many textbooks that we always put the quantum mechanics in the very beginning. But I hope that after this chapter, you probably can get a little bit sense that with applying the quantum mechanics is not trying to complicate our life. Actually, just try to help us to understand the system, the semiconductor system, because inside the semiconductor system, some of the phenomena cannot be understood using the classical physics. Although we already have a basic physics-based speculation, we can imagine how these electrons movements inside this system. But for the scientific consideration, we need to have the more rigorous proof, and therefore the quantum mechanics come in to prove what we have understood so far is reasonable. And then there's a solid foundations behind. There's a solid foundation to support these mechanisms. Okay, so that's the end of this chapter. So we have been talking about how to this basic foundation for the quantum mechanics, how we can leverage quantum mechanics to help us. So now for sure that we will start to extend to the case that we are particularly interested in, especially inside as a solids here. So therefore in this chapter we'll be talking about the quantum series for the solids. So in this chapter, we actually try to understand that the issues that we have been mentioned, that the concept we mentioned are related to the energy bands, this kind of the band gap, this kind of concept. So here is the learning outcome that you will be able to understand after this chapter. So after this, you will be able to explain the origins of the energy band, describe how this discrete energy level split into the allowed and forbidden energy band when the atom formed as a periodic lattice, and also you are able to explain the formation of a valence band, conduction band, and band gap energy. I think that would be the most important concept that how we can use what we knew so far in the end to have the knowledge help us to form as a concept related to the forbidden band, allowed band, and also the conduction band, valence band. And also, there's a very important relationship that we call the energy wave relation. So we are able to analyze the EK diagrams and explain their significance in the semiconductor physics. And also the curvature of the EK diagram is related to the effective mass of the carriers. And also with consider the EK diagram, we can distinguish there's a semiconductor material that has two different types of band gap. One is a direct, another is the indirect band gap semiconductor. So this direct and indirect band gap semiconductor will highly influence the semiconductor material property and their application. And also, in this chapter, it's very important that in the end, we will talk about the carrier statistic. Why we have to consider the statistic? Most of you have already learned the statistic in the high school, or probably after you come to the university, you don't use the statistics quite often anymore, 统计学, unless you try to follow some economic or finance class, you probably will learn the statistic. But in semiconductors, the statistic is very important. This is because of the fundamental issue is that we cannot determine the semiconductor carrier. We cannot determine the electron holes precisely. We can know their behaviors in terms of the probability. So once you need to estimate the one electron holes, they have the probability, this kind of a characteristic. You need to apply the statistic. That's why we need to use the statistic knowledge to estimate the probability of the carriers. That's why the carrier statistic is very important. So we will explain the concept of density of state, DOS. Once we know the density state, finally we can start to have the estimation of the carrier concentration, because in the end we are interested for sure. We're not that interested of the probability, we're not that interested of the statistic, but we definitely will be interested in inside a piece of semiconductor material, what is the concentration, because our goal is to estimate the concentration. Because many equations in the end all tell us how to estimate the concentration of a semiconductor in the one particular region. But before we reach to that point, we have to apply the statistic state by state to analyze probability, density state. Finally, we come out with a series to estimate the concentration. And also, we have to consider this Fermi-Dirac statistic to estimate the probability. And then also, we have to understand the physics meaning of this Fermi energy, which is very important for the Fermi energy, because in the end, after this chapter, we won't talk about what's the definition of the Fermi energy. We'll just apply the Fermi energy, especially if you already have the experience that start to look at the literature, look at the work on semiconductor, run some simulation. The Fermi energy is definitely the one that you will talk about, discuss every day at night, because this is a key energy level that highly determines your semiconductor materials property. Okay, so let's start to go back to the one by one, to come back and then to first to consider that how do we understand the energy bands here? So far, we only talk about there's a semiconductor material, there's atoms in the group 3, 4, 5, and they were placed in the very periodic arrangement become the lattice, and then we talk about quantum mechanics, quantum tunneling. But how do they form as a band? Because if already not that new for the semiconductor, you probably already know about the band, this kind of concept. But still, we need to come back as a little bit fundamental to understand this. So, the formation of energy band, this is because the wave function of electron of the two atoms overlap, which means that the two electrons will start to interact. So imagine now you have the two atoms. You try to put as close with each other as possible as you can. Then the wave function for each atom will be overlap with the neighboring atom that has their own wave function. And therefore, this means that the electron will start to interact like here. So you have one atom has their own wave function. So this is one atom. But now you have another atom, and you try to place these as close with each other, and you start to have these interactions here. So the interaction or perturbations result in the discrete quantized energy level. So that will be spelling this in the two discrete energy level as shown here. To really prove this concept, there's a very dedicated equation to prove that one. So I believe that you can find lots of material that try to prove this one. In here, we just try to summarize as a conclusion. If you are curious at how this insight, I know it's difficult to imagine probably at this moment, but if you are curious how this happening, you can look at the fundamental textbook that describes it here. But in the end, the conclusion that you will have this discrete energy level formation as shown here. So now if we somehow start as a regular periodic arrangement of a hydrogen type atom that initially very far away but began pushing the atom together, the initial quantized energy level will split into a discrete energy level, and this is shown in here. This will be split into the band of the discrete energy level. Because in the previous case we talked about the two atoms, but now you have the lots of atoms inside this periodic arrangement inside the lattice. Then therefore all the interaction with the wave equation will split into not as a two energy level, but will split into the band of the discrete energy level. So that will be shown something like this one. So this is a band, and inside the band you have the many different energy level here. And this is because now you consider that you have a lot of atoms, that inside you have a one atom, but nearby has a lot of atoms, and lots of wave equation will be interacting with each other and then splitting in the band. So each atom now contains more than one electron here. So suppose the atoms in the crystal contains electron up to 3. n equal to 3 energy level, then we can expect that there are the 3 energy bands as shown in here, as one each 3 band inside has a discrete energy level. So, to further consideration here, that if we only consider the n equal to 3 level for the valence electron, since the first 2 energy shells are completely full, are tightly bonding to the nucleus. So the 3p state corresponding to n equal to 3 and L equal to 1 and contains 6 quantons per atoms here. And therefore, we have the 6 allow energy at the same level. And then the 2 allow energy at the same level as shown here. So this is coming from the knowledge from the typical understanding of the electrons and in the shell of the one of the atoms here. So as distance decrease, so we have to start to put the atoms close to each other. The 3s and 3p will interact and overlap with each other. And now at the equilibrium interatomic distance here, the bands have again split, but now we will have a 4 quantum state per atom. So the 4 quantum per state or atoms in the lower band, which is here. And also, we have a 4 quantum state per atom in the upper band, which is here. To simplify this drawing, as you can see that this drawing is very complicated. So original at the 3p, you have a 6n state, 2n electron. At the 3s, you have a 2n state, 2n electron. The ones getting too close to each other. So overall, 6 plus 2 will be equal to 8. And then we'll split into the 4n on the top and 4n on the bottom. And of course, we now have the 2n electrons plus 2n electrons. They will prefer to stay in the low energy. So this 4n state will be occupied by 4n electron. But the upper state has a 0 electron. But this drawing, just way too complicated, cannot be reproduced or can be easily drawn time to time. Therefore, we try to reform this drawing as a more simple way. We define this as the top, and we define this as a bottom, and in between we consider as a EG, that's a band gap here. Therefore, we redraw this schematic in the way that more easily drawing. We just put this as a flat here. So therefore, we still the same. The top is a EC, where we consider this one is a EC, and the bottom is a EV. Then we consider the bottom as a EV here, and the difference between the EC and EV is equal to EG, which is this one, right? So that's is band diagram that you are very often to see in the later discussion. But the original was coming from this little bit ugly drawing, but just try to reform this drawing as a way that we are more easily to draw and to interpret. So we just put them as a flat here. So this become as what we knew as a band diagram. And then the difference between in this region, now you see the electron all stay here, right? So we have a foreign electron stay in below. So this suggests that this electron, we have a foreign electron here. And then on top, we have the 0 electron. So we don't have any electron here. So therefore, we have 4 electrons below the EV, and we have the 0 electrons above the EC, and there's no any electrons between here. So this means that ideally there's no electron in this region between the EC and EV, and that's why we often call this as a forbidden energy band. Because this is a region that suppose there's no electron existing, right? The electron is only stay below EV and empty above EC, and ideally we should not find any electron in here. So that's why we call this region has another name that we call the forbidden energy bands here. And compared to the forbidden energy band, that means this region and this region should be the region that we are possible to allow the electrons existing. So therefore, we call this region and this region as a allow energy band, which is also here. So we have the particular name called the allowed energy band. So that's why later you will see we only draw this schematic. We call this forbidden energy band. We call this allow energy band, allow energy band. But one thing we still will have a particular name is that this region is a region full of the valence electrons. So that's why we call the valence band. So that's why we have a name EV here. The V is called the valence. But why we call this C? This C is called, this C, it means a conduction band. And then we will talk about later why it's called conduction band, because once you have an electron jumping from the valence to the conduction band, you start to have the carrier movement, you start to have the electricity. So that's why this is an empty region that electron can conduct it. So that's why we call this as a conduction band. So similarly, once you understand, you almost can forget this anymore, because in later discussion, we won't draw the band diagram using such complicated drawing. We only consider the band diagram as here. But of course, that's why we spend this effort from here to here. But once you understand, normally in the future, we will only show this. So, as a summary, in the next slide, so finally, our knowledge is starting gaining the knowledge from the atomic level, that we have the two-wave equation close to each other that split to the band, and then we have a bunch of the periodic atoms that will split to the several bands. And then with this understanding, we can build up the band diagram where we have the top that we call the EC, the bottom that we call the EV, and the difference between the EC and EV is we call the band gap, EG. And sometimes, as a previous knowledge, we understand that the electron can only stay here and here, but not possibly here. So that's why we also call this as a forbidden energy band. And also, because the bottom is the below the EV is a state that with a full of electron. And then the top is empty without any electrons here. Now we define the bottom with a full of electrons that we call the valence band. And the top we call the conduction band. So, in the case of absolute 0 degrees, electrons are in the lowest energy state. So the older state in the lower band, valence band, will be full, and the old state in the upper band, conduction band, will be empty. The band gap energy, e.g. between the top of valence band and the bottom of conduction band, is the width of a forbidden energy band, as shown here. This one is called the band gap. That's also, this region is called the forbidden energy bands. Okay, so we will take a break and then come back with 10 minutes later. Okay, so in this slide we'll discuss this very famous, as we call the chronic penny model. This is a model for the one-dimensional periodic potential function used to a single crystal lattice. So this is considered that in the previous case, we only consider, like, for example, one of these or one of these. But now in reality, for sure that we have the periodic autons, and therefore in reality should have this periodical potential function. So as with previous quantum mechanical problems, the most interesting solution occurs for the case when energy smaller than V0, which corresponds to a particle being bonded with a crystal. The electrons are contained in the potential wells, but we have the possibility tunneling between wells. And this model is idealized. This is ideal periodic potential representing a one-dimensional single crystal, but result will illustrate many of the important features of quantum behaviors of electrons especially in the periodic lattice. So that's the purpose. That's why we have to introduce this model that's consider that there's a periodic potential, and then to understand the quantum behavior electron in the periodic lattice here. So that's all. In regarding for the detail of this model, we will only mention up to here. That's just a kind of the introduction that this model is trying to help us to understand in the case with a periodic potential. But for the future, that further interesting that further consideration for this model, that if you are interested in, that you can look at the textbook to look at for more details. So another important concept is what we call the K-space diagram. So as we previously already shown that the K is equal to here. So the constant of motion parameter K is related to the particle momentums for the free electrons here. And also the momentum and the wave number are linear related. And therefore, with a consideration of this calculation, where P is equal to mv, and then we can have this equation out. And in the end, we can have this one. So that will lead to this equation. N star is equal to 1 over h square here. So that will be equal to this one. And especially, this is the second order of the derivative of the E versus K. And especially this term suggests that the effective mass so therefore, the curvature of E versus K diagram near the minima of the conduction band energy is related to the effective mass of the electrons. So that's we can use this derivative to calculate the effective mass. That's how we can conclude from this K-space diagram. So now, as our goal still in the end that we will be interested in the electrical conductions in solid. We are not only interested in the atomic behavior, but in the end we want to know how to understand the conduction, which means that like the current, and then also how to estimate the current, how to estimate the concentration. So let's start to further have a certain knowledge based on what we know. So in the previous case, we discussed that once we have this electron moving inside this lattice, now we can reform this knowledge into the consideration inside the band diagram. So therefore, in the previous, we have been shown that the EC, EV, EG, and the electron moving from one place to the other can be also considered inside the band diagram, where we have the electrons in the valence band that jumped over this forbidden energy band into the empty conduction band. And this behavior will cause the current, which is exactly this electrons movement contributing. So now we transform this understanding as a carrier electron movement inside the lattice contribute the current become as this band diagram where we have the electrons in the valence band jump over the band gap, reach to the other side. As long as they can jump to the empty conduction band, this carrier, this electron will start to contribute as a current here. So the energy state in the valence band are completely full. So this will be completely full and completely empty, and this is how we also define as a EC, EV. So this is the same that where we have been already shown just in the EK diagram here. And for temperature larger than 0K, some electron might gain some energy to jump to the conduction band and have left empty state in the valence band. So once the temperature is larger than 0K, the carrier, the electron will gain some thermal energy, and therefore the carrier will start to jump. The carrier will start to jump and then become the current. So that's how actually the current form with considering by using this EK diagram. And the same can be also understood by considering this band diagram as well. So therefore, finally, we can have this understanding that with one material, for example, silicon, then we have one silicon has their own band gap here. If the electrons in the silicon want to contribute as a current, so the electrons in the valence band should jump over the band diagram, and this jump over the forbidden band, and this will contribute as a current, for example I1 here. But now if we look at another material that has a larger band gap, for example Eg2 here, and this can be the case, for example, like the diamond. And again, we have the electrons below the valence band, and if the electrons want to contribute as a current, the electron need to jump over the energy band and reach to the conduction band. That becomes the I2 here. But since Eg2 is larger than Eg1, and therefore the probability for the electron here to jump over Eg2 will be much smaller than the electron here jump to the conduction band in the silicon. Since the probability here is lower, the probability is higher, therefore we can foresee the current of I2 is smaller than I1. So that's an implication that how this band gap, the band diagram can tell us, and that's why the different material has a different band gap, and then that will cause a different and current. And some more information for the K-space band diagram. In the reality, this is how the K-space diagram look like. And then we can see that there's a possible that the K-space diagram where the top of a valence band and then the bottom of the conduction band, they are aligned with the same K position, and this is a material that we call the direct band gap. And in this case, the electrons can be directly jumped across the forbidden band and reach to the conduction band. And then, however, there's a certain material, something like this one, that the top of valence band and then the bottom of a conduction band are not aligned with the same K position. Therefore, means that if the electrons want to jump to the conduction band, first they need energy to jump in, and also need the K, which is momentum. So this involves the two steps. First, you need enough energy and also enough momentum, K here. And this is a material that we call the indirect band gap. And then one of the most famous indirect band gap material is silicon. And one of the famous direct band gap material is gallium nitride. And because of this direct band gap, this unique material property, that the electron can be more efficient to jump to the conduction band without any need additional momentum. So this mechanism makes the gallium nitride is very suitable for the light emitting diode LED application. And because we only need energy, but the silicon need energy plus momentum, so that's not needed. That's require two-step process, and therefore you will never see silicon will be suitable for the light emission application. Okay, so the overall goal for us is for sure that in the end we still need to somehow find a way to derive the equation for the current. So the current is due to the net flow of the charge. So we have the current. This is average. Consider average drift velocity. This is considered the individual ion velocity. So if a force is applied, it's a force applied to a particle, and then the particle moves, it must gain energy here. So once there's a force applied, you will see like this one, they will become the asymmetric distribution. Of electrons in the E versus K diagram when there's an external force is applied. So as state here, if an external force applied to the electron in the conduction band, there are empty energy states which the electron can move. Because of this external force, then we can start to foresee there will be the drift current due to this asymmetric distribution. So before we can reach out the knowledge to estimate the current, we need to first to know how to estimate concentration. Before we have the way to estimate concentration, first we need to introduce a concept that we call the density of the state function. So sometimes we just call this as a DOS. The density of state, which means that this is a function, this is the purpose, the function that mainly we are addressing the issue of a probability density function. So we are interested, since we have a probability density function, but we are interested in that in the certain state, what would be the density? So that's why we call the density of state. The density of state is, if you look at the Mandarin textbook, that I actually didn't know how they do the translation, but in anyhow, even you try to translate in the Mandarin, it's still difficult to understand. In the short, it's just that since we have a probability density function, but we want to estimate the particular density in the one particular state, that's why we have this density of state function. Since the current is due to the flow of a charge, an important state in the process to determine the number of electron hole that will be available for conduction. So because in last slide we know that the current is mainly due to that you have a charge. So the next question is that we need to determine that the number of electron holes that will be available for conduction. The number of the carriers that can contribute to the conduction process is a function of the number of available energy or quantum states. Because first you need to make sure that you have the energy state, and therefore once you have energy state, the electron might start being possibly stay in the state, then that will become the available electron and holes. So that's why the questions become that first we need to understand the state. And once we understand the state, we know that the maximum possibility, like how many electron hole will be available. Just like in the case, if we want to estimate how many students in this room, first we need to understand how many available seats in this room. For example, in this room we have roughly like 120 available seats. That's an available state. Once we know this available state, we can possibly to make the statistic to estimate how many students in average in this room. So that's the same ideas. So therefore, the question is become that we must determine the density of least allowed energy state as a function of energy in order to calculate the electron and hole concentration. And then the density of least allowed energy state is what we call the density state. So, for example, this is our band diagram. We have EC, EV. We don't know how many electrons, but first we have to determine estimate how many allowed energy state here. So these are the allowed energy state. So once we know how many energy states, so then some of the state might be occupied, or all of them might be occupied. So therefore, we are able to estimate the number of electrons. Also, we have this so this will be our allowed energy state, but right now it's empty. And then some of the electrons are being jumped here, jump over and start to occupy. So therefore, by considering this, first we need to determine the density of least allowed energy state, which in short we call as a density state here. So that's a purpose that why we have first to understand how many density state, and then with a certain statistic we are able to calculate the concentration. So first of all, the density function. The density of the quantum state is a function of energy, is shown here. As the energy of least free electron becomes small, the number of available quantum state decrease because of this equation. And this equation, I can understand it's difficult to understand, but it's more straightforward if we just use a figure, use a plot to illustrate the behavior of this density state function. So first of all, we have the conduction band. We have a valence band here, and then this is with as a y equal to the energy. So the first is the density of allowed electron energy state in the conduction band. So if you try to plot this one, this is GCE, which has this E minus EC correlation. If you try to plot, then you will get the density state function, which will be equal to this one. That's a GCE. And similarly, we have a density of allowed electronic energy state in the valence band, which will be correlated to the EV minus E, and therefore we have the density state function like this one, which is a GVE. So that's the curve look like that how this density state function above the conduction band and below the valence band, because of in the region between EC and EV, this is a forbidden energy band, so there's no allowed energy state in the between the EC and EV, only happen above EC or below EV. So the next phase is that we has to apply some statistics. So in dealing with a large number of particles, we are interested only in the statistical behavior. We are only interested in the statistical behavior of the group as a whole, rather than the behavior of each individual particle. So we are interested in like the overall statistic behavior for the carrier, rather than the individual behavior for each particle. So therefore, we have three well-known statistic laws that are very often that being used as a science and the engineers. The first one is Maxwell-Boltzmann probability function, which is described here. Fe is equal to exponential minus E minus EF over KT. So the particles are considered to be distinguishable by being numbered with low nominal number of particles allowed in each energy state. So that's only applied to the gas molecule. Because there's no limit of the particle allowed in the energy state, which means that in the one state you can have the 1 particle, 2 particle, you can have 5 particle, you have a 10 particle. This can be only considered the case like in the gas, because for example in here we have a 126 for the seat available, but we can have as many as a gas in this room. So that can be used as a Maxwell-Boltzmann probability function. And the second one is more important for us, is a Fermi-Dirac probability density function, which is shown here. One over 1 plus exponential E minus EF over KT. So the particles are again indistinguishable, but now they only one particle is permitted in each quantum state. For example, that's the case as an electron in a crystal. So if we consider electron in the crystal, that would be this case that only one particle is permitted in each quantum state. So then, therefore, Fermi-Dirac probability function is more suitable for our case. And there's a third one. So this one is more important. And the third one is a Bose-Einstein relation function, which that we have F E is equal to 1 over exponential E over KT minus 1. And this will be more suitable for the case as photons here. Since there's no limit to the number of the particle per minute in the quantum state, and then these particles are indistinguishable. So that's why it's more suitable for the case of photons. But anyhow, Fermi-Dirac probability function is the one that we will apply in our case. So if you look at the Fermi-Dirac probability function, we have several terms that need to explain. The first one is this function can be considered as a NE over GE, where the NE is the number of particles and then the GE is a number of a quantum state. So number density Ne is a number of particles per unit volume per unit energy. And then the function GE is a number of quantum state per unit volume per unit energy here. So anyhow, this is the number of a particle over the number of a quantum state. And then the EF here is what we define as a Fermi energy. So the next stage we start to discuss some more about the case of this Fermi-Dirac probability function. So in the case of t equal to 0k, and we consider the case when energy is smaller than EF. So therefore, this exponential E minus EF over KT will be equal to exponential minus infinity will be equal to 0. And therefore, this will become 0. And then this term will become 1. So which means that if you consider the EF here, and when the case of the t equal to 0k, this is EF, and when the case t equal to 0a, and then the energy below the EF, the probability is equal to 1. This is equal to 1. And the second case, when energy is larger than EF, this will be equal to 0. And therefore, this will become the case here. And if the E is equal to EF. And therefore we will get this equal to 1/2, which is here. So that's why you will see this is FE versus E, and then the full curve will be somehow look like in this way. This is at the case of T equal to 0K. So if you consider that there's a one system contain for 13 electrons here, and then we have a different energy, and then based on this case, the Fermi energy must be below E4, above E4 but less than E5. So where we will have this here, this will become our Fermi energy. So the below the Fermi energy is a field. And above the Fermi energy is empty. And the reason why we can get this is coming from the previous slide, right? Below is a field. Above is empty. So if you transform this figure, consider the case, this all field, this all empty. So therefore, the Fermi energy must be located at here. The electrons are in the lowest possible energy state, so that all the states below EF are filled. And then all states above EF are empty. So in this case, this is a GE or NE versus E here. So this case, this is EF. And therefore below EF are all filled. So which will be the case here. And above EF will be equal to empty. So try to think about in different angles. In the end, that every angles are very consistent. It doesn't change the conclusion. Still, everything below EF are filled, everything above EF are empty. But this only considers the case with the T equal to 0K. But in reality, we never have the T equal to 0K. It's always the temperature will above the 0K. So in this case, the electron can gain certain amount of the thermal energy. So therefore, some electron can jump to the higher energy level, which means the distribution of an electron among the available energy state will change. So from the previous slide, we knew that the EF is here. But now, because of a temperature is increased, therefore, the electron will gain some energy. Thermal energy will start to jump over the EF, and therefore, the above EF is not completely empty anymore. So this will change the available energy state here. The change in the electron distribution among the energy level can be seen by plotting the Fermi-Dirac distribution function, where we previously shown In the previous slide, we shown that this is FF E over E. At the t equal to 0 case, we have the plot like this one. But now, this is a case of a t equal to 0K. But now with the temperature increase, we start to see that there's a possibility that this one has electrons being filled. This has the state being empty. Therefore, this drawing will become like here. This will decrease, and this will increase. This is because this is as a case of a T1. This is because of some part of the electron jump to here, so that this layer has an electron, layer has a state being empty, there has a state being filled here. And with further increase of temperature, this shape will become like here. So this is a case for T2 here. So as the temperature increase, the probability of energy about EF being occupied increase. Increase as the temperature increase. So that's why we will see the increase of this in this region. So this is a consideration of the T2 larger than T1 larger than T. So that's almost everything we need to know for the Fermi-Dirac probability function with considering the electrons and then the quantum allowed energy state. And sometimes we will do some approximations that if we consider when the E minus EF is much larger than KT, that's we call the Maxwell-Boltzmann approximation, and this original function can be rewritten as FFE exponential minus E minus EF over KT here. And we consider this approximation, we can have this curve here. And this will be only valid in the case of E minus EF much larger than KT. So that would be similar to the case like our original Fermi-Dirac functions. Sometimes we will consider this Boltzmann approximation. So that's also some part of the basics for this Fermi-Dirac probability function. So that's all for this chapter. So this chapter is mainly talk about the energy bands. The first one for sure to understand how do we form the energy band. That's the idea is that when there's atoms come to close very together, then we will start to see the discrete energy level split into the bands. That's because of the wave functions overlap here. And this will lead to the concept of a valence band, conduction band, forbidden band gap. And that's also in the end to determine the band structure. And then the electrical behavior of the materials depends on the band structure here. So semiconductor, we have a smaller band gap. Insulator, we have a large band gap. And conductors, we also have these overlapping bands here. And we have a difference between the direct and then the indirect band gap. And when we consider the electron motion in crystal, we have to describe by using this EK diagram, and then the curvature of EK determine the effective mass. And if you already have a little bit experience, then you will see that the effective mass in the end will influence the carrier mobility. You will see that lots of the basic equation for the carrier mobility is all correlate with the effective mass. And regarding for the carrier statistic and conduction, so the charge transport in semiconductor is mainly because we have electrons in the conduction band and holes in the valence band. That's because of the motion of this. And then once we apply external field, that will create the drift velocity. That will create the drift velocity, and that's in the end cause the current here. But before we can start to estimate the current, we need to first to understand the concentration, how to estimate concentration. But before start to estimate concentration, we first to come to the fundamental statistic equation that are related to the density of the state. So the density of state describes the number of allowed state being available at each energy level. And the carrier concentrations depends on DOS and then the occupation probability. And since now we are not interested in the one individual carrier, we are interested in a group of a carrier as a whole behavior of the group carrier, and also consider as a probability. So therefore we have to introduce this Fermi-Dirac statistic that give us a way to determine the probability that the energy state is occupied by an electron. So later, with a combination of what we knew for band structure, density state, and Fermi-Dirac statistic, this will give us a way finally to estimate the carrier concentration. So once we can estimate the carrier concentration, for sure, we can start to estimate, to determine the current. So which will be explained in the next chapter. So I hope that by end of this chapter, you can understand a little bit more logic behind that how this content being arranged, why we have to talk about this statistic, because these all the fundamentals need for us to understand the concentration and the current here. So we will stop the class here, and then next week we don't have a class, so that we will be off because I will be out. And then we will see each other 2 weeks later, and we have also the makeup class on the 2 weeks later at one of the Wednesday in the evening. And also the 2 weeks later we have the homework.